Hi everyone. Today we're going to talk a little bit about how a neuron creates the signal that travels down its axon. Last time we kind of talked about the parts of the neuron and all that good stuff. As a quick review, here we've got an illustration of a neuron, cell body, dendrites receive the signal travels to the cell body, a new signal is created here at the axon hillock, which travels down the axon to the axon terminal. The cell that receives that signal is called the postsynaptic cell. It's separated from the axon terminal of the neuron by a small space called the synapse. And we need to talk about how the neuron is able to create that signal. Finally, these blue circles, those represent the Schwann cells associated with that axon that speeds up the signal. Okay, so before this axon can fire, a very specific set of conditions need to be established inside that axon. Okay, and so that's what I'm going to describe here. Imagine that we're going to take a little chunk of this axon and we're going to zoom in on it right over here. So this is the axon, a little chunk of it. This is the outside of the axon, this is the inside, and this is the outside. Well, it turns out that there's a lot of potassium, K+, located on the inside of the axon, and just a little bit of potassium located on the outside. And at the same time, there's a lot of sodium in orange on the outside of the axon, and there's just a little bit of sodium on the inside. And the cell actually wants to move more sodium to the outside and more potassium to the inside. Now, because that is exactly opposite of what sodium and potassium want to do, that is going to require energy to move the sodium out and the potassium in. Like the potassium wants to move out due to diffusion. He wants to spread out from an area of high concentration to low concentration. Same respect, sodium wants to move in. The cell wants to do the exact opposite. So if we're doing the exact opposite, we need a pump to move those ions against their concentration gradient. That's the sodium-potassium pump. Every time that sodium-potassium pump consumes a molecule of ATP, he's going to move 3 sodium ions out, and he's going to move 2 potassium ions in. And that takes energy, okay? Now, before we kind of go any further, we need to talk about the charge that exists inside this axon. Here is a graph that is going to measure the voltage inside the axon. Now, think of voltage as just charge. That's whether or not you have a positive distribution of ions or a negative kind of distribution of ions inside of the cell, right? If there's more negative things, there's a negative charge. If there's more positive things, there's a positive charge. Right now, the charge is 0 because both of these ions have a positive charge and everything's pretty much balanced. We also have some negative ions like chlorine that I haven't drawn. But right now, things are pretty much balanced. Positive on the inside, positive on the outside. But there's something else going on. This cell membrane, right here and right here, is slightly permeable to sodium. Okay, and what that means is that there's these little channels that sodium can leak across if it wanted to. Well, we know that sodium wants to leak across. And what that means is that there are these little channels that will allow potassium to leak across if it wants to, right? We know that potassium wants to leak across because there's a lot of potassium on the inside, there's not a lot of potassium on the outside, so potassium is going to do just that. It's going to start leaking across these channels. That's what these dotted lines represent, potassium leaking across. Well, potassium has a positive charge, and when potassium leaks out of the axon, it's going to cause the charge of the axon to go down. It's just like your bank account. If you have positive things leaving your bank account, the balance is going to go down. So it's going to drop down all the way down to about negative 90 millivolts. By the time it reaches negative 90, potassium still wants to leak across, but the negative charge inside the axon is going to kind of help attract some of those potassium ions, and so it really gets down to about negative 90, and that's about it. Now, at the same time, sodium also would leak across if it could, and it turns out that the membrane is also slightly permeable to sodium. Not nearly as permeable as it is to potassium, but a little bit of sodium can leak across, and that's exactly what's going to happen. Sodium is going to leak inside the membrane. I'm only drawing one arrow because not nearly as much sodium is going to leak inside. Well, when sodium leaks in, that's going to cause the charge to increase because sodium has a positive charge inside the axon. So comes up a little bit. But it doesn't go all the way back up because just a little bit of sodium's leaking in relative to the large amount of potassium leaking out. And once that happens, everything's pretty much balanced and it stays at about negative 70 millivolts. Okay? It's a balanced situation, but it's very dynamic. You got potassium leaking out, sodium leaking in. You've got the sodium-potassium pump moving the ions back to where the cell wants them to be, and everything stays at about negative 70. It's like a leaky boat. It's like you're in a boat in the middle of a pond or a lake. You got water coming in. You want to stay out there, so you have to keep bailing it out if you want to stay afloat. Well, this very balanced but yet dynamic situation is what's called the resting potential. And that is what needs to be established in order for this neuron to fire. Okay? So in order for any neuron or any axon to fire, this negative 70 resting potential needs to be established. So let's think about that. Even when every neuron is at rest, every axon of every neuron of all the billions of neurons in your body are doing this 24/7, even when they're not firing. They're spending all this energy through the sodium-potassium pump to establish this resting potential. That's why neurons are so expensive. Okay. So now let's talk about what happens when this neuron actually does fire. Well, I'm going to redraw. What I've done is I've redrawn the same section of this axon right over here. Okay, and I've drawn some new proteins. We've got a lot of sodium on the inside. We've got a lot of potassium on the outside. Okay. Well, the sodium-potassium pump is not the only protein that's in the cell membrane. Here I've drawn a bunch of voltage-gated channels. In orange, we have sodium voltage-gated channels, and in green, we have potassium voltage-gated channels. Now let's think about what this means. A channel is obviously a pathway for an ion, okay, or a chemical. In this case, these orange sodium voltage-gated channels, these are channels for only sodium. Nothing else can go through. And in the same respect, the potassium voltage-gated channels, only potassium can go through. Voltage-gated, what that means is that these guys, what determines whether or not they're open or closed is the voltage inside the axon. At the resting potential at negative 70, all of these voltage-gated channels are closed. But there's a magic voltage that's going to cause these guys to open. And that magic voltage is negative 55 millivolts. So let's consider the sodium voltage-gated channels first. When the charge inside the axon reaches negative 55, those sodium voltage-gated channels are going to open up, right? And let's imagine that's exactly what happens. Let's imagine the voltage inside the axon goes up to negative 55. That's going to cause these sodium voltage-gated channels to open. And sodium is going to want to fly in. It's going to want to fly in for two reasons. Number one, it's going to want to diffuse inside the axon because there's a lot of sodium on the outside. It wants to move in to spread out. But the other reason sodium comes in is the chemical or the electrical gradient, That's because the charge inside the axon is negative 55. Sodium has a positive charge, opposites attract, sodium flies in. As sodium flies in, that's going to cause the charge inside the axon to skyrocket all the way up to positive 30. After that happens, these sodium voltage-gated channels automatically close. When they open up at negative 55, they're only programmed by design to stay open for a short amount of time, a millisecond or two, after which they close off, right? There's no more movement of sodium. Well, remember those potassium voltage-gated channels? Those responded to the same threshold voltage. So when they experienced negative 55 inside the axon, they also opened up, but by design, they opened up after a short delay. A short delay of 1 to 2 milliseconds, they're going to open up right here at the same time that the sodium voltage-gated channels close. So as soon as the sodium voltage-gated channels close, these guys open up. Now potassium is going to want to leave. And it's going to want to leave for two different reasons. First, you're going to have the chemical gradient that causes those ions to leak out. Second, you're going to have the electrical gradient. Right now, the voltage inside the axon is positive. Potassium is also positive. Two positives repel each other, so potassium is going to leak out quickly. As potassium leaves, we have a positive thing leaving the axon. That's going to cause the voltage to drop all the way back down to negative 7. After which, these potassium voltage-gated channels close. Some of them are slow to close, though, like that last one. He might not close right away. And that's going to cause the voltage to overshoot negative 70, maybe go down to negative 80 or 90. Eventually, all the channels close, and the resting potential is reestablished. The protein pump starts moving things back to where they should be. Everything's still leaking, and we reestablish the resting potential. Okay. Now, I'm going to draw another action potential real quick so we can kind of review the steps that we just talked about. When the voltage inside the axon reaches negative 55, the sodium channels are the first to open. So sodium channels open. That is going to allow sodium to come in, which causes the voltage to increase all the way up to positive 30. When it reaches this point, the sodium channels close. At the same time, the potassium channels are going to open. That is going to allow potassium to come in. The potassium channels close right here. Okay. And this whole curve that we have described, both here and here, that is called the action potential. And that is the signal that exists inside of a neuron. Okay? Or inside of an axon, excuse me. A little bit more terminology here. When an axon is at the resting potential, it's considered to be polarized. That's because it has a negative charge inside the axon relative to the outside world. Anything that's polarized just has a negative, has a difference in charge, right? From the inside to the outside. Like a battery is polarized because it has a positive side, negative side. At the resting potential, the axon is polarized. During the first part of the action potential, as sodium comes in, that's called depolarization because we're losing that polarity. It's going to basically zero. As we regain that negative charge, that's called repolarization. And then as it overshoots due to some of those potassium channels being slow to close, that's called hyperpolarization. Okay. So that's good, but we still haven't explained why this travels down the length of the axon. We've just talked about the action potential occurring at one specific location. Well, let's consider this same section of the axon. And let's imagine that everybody is at the resting potential before an action potential occurs. So everybody's at negative 70. And let's imagine that the action potential occurs right here in this little part of the axon on the left-hand side. If the action potential occurs there, the charge is going to skyrocket from negative 70 to positive 30. Now, charge is a funny thing. It's a lot like heat. It spreads out a little bit. Like if you had a space heater in the front of the room, put it on high, it wouldn't really heat the room very evenly. You would have a hot region up here, and it would get gradually colder the further you got away. Same thing happens with charge. If we've got the action potential that occurs here, it goes up to positive 30. Do you think it's going to be negative 70 still, right next door? Nope. This charge is going to spread out a little bit, and it might elevate this guy right next door up to about negative 55. Well, the significance of that's this threshold voltage. If it goes up to negative 55 here, it's going to cause these sodium channels to open, which then triggers the action potential. So he goes up to positive 30. If he goes up to positive 30, it's going to spread out, raise him to negative 55, which causes the action potential to occur here, and then here. You can kind of get the idea. It's this chain reaction that flies down the length of the axon, and that's the signal of the action potential. That's how it kind of travels down the length of the axon. Okay, and that's another reason why it's not that fast, right? So it's going to be a heck of a lot faster than the electricity in your wires in your home, and that's why it travels at about 25 miles an hour or so, because we're waiting for channels to open, we're waiting for ions to diffuse across that membrane, and it takes time. And so the action potential is fast, but it's not super fast. Now, a couple things about the action potential before we finish is that, number one, the action potential for a given neuron is always the same size. It always ranges from about negative 70 to positive 30, and it always goes at the same speed. However, a single neuron can tell the brain and the central nervous system whether a stimulus is small or large, so it can encode the magnitude of a stimulus. How does it do that if the action potential is always the same speed and always the same size? Well, it does that by encoding the frequency of action potentials. Let's say this is a neuron over here that's encoding pain from one of your nociceptors. And it's going to try to tell the brain that it's experiencing a lot of pain, right? That you've injured yourself. If that's a strong stimulus, so a lot of pain, that neuron is going to fire as many action potentials as it can over time. And that high frequency is going to tell the central nervous system that the signal is strong and that there's obviously a big problem. Okay. Now, final thing I wanted to mention is that these Schwann cells and the peripheral nervous system can speed up the rate, or can speed up the action potential. It does this because if you've got Schwann cells, the only places that you can have these voltage-gated channels are in the little tiny spaces between the Schwann cells. Those are called the nodes of Ranvier. You can't have channels here underneath the Schwann cells because they're covered up. So if the action potential occurs here at these channels, this is going to go all the way up to positive 30. The Schwann cells do a great job of insulating that heat so it spreads out further down the length of the axon. If it goes to positive 30 here, it's going to be able to raise the voltage all the way over here at the location of the next channels up to threshold, negative 55, so that these guys experience the action potential, and then these guys, and then these guys, and these guys. It causes that action potential to jump down the length of the axon between those Schwann cells, whereas in a non-myelinated axon, one that doesn't have Schwann cells, it's going to more smoothly kind of proceed down the length of the cell. And that's a really quick kind of overview of the action potential. Thank you.